Hello everyone. Today I'll be presenting our work, PhaSR, Generalized Image Shadow Removal with Physically Aligned Priors, accepted to CVPR 2026, with authors Jiaming Li, Yufan Lin, Yuro Xiao, Jinhui Jiang, Yulin Liu, and Qi Chengxi from National Yangming Chiaotong University and National Cheung Kong University. Shadows are ubiquitous in real-world images and significantly degrade downstream tasks such as autonomous driving, remote sensing, segmentation, and 3D reconstruction. Since shadow appearance varies with light source direction, intensity, and viewing angle, the same object can look drastically different under different conditions, creating a fundamental ambiguity between shadow-induced darkness and intrinsic material darkness, making reliable visual recognition extremely challenging. Here's a concrete example. In this Tesla full self-driving video, the vehicle misinterprets a wire shadow on the road as an obstacle, causing unexpected behavior. And Tesla's owner's manual explicitly warns that autosteer may fail when strong shadows fall on lane markings. Confirming shadow removal is an unsolved real-world challenge. Looking at how the field has evolved, traditional methods relied on a two-stage pipeline, shadow detection followed by mask-guided restoration, which is fragile and dependent on detection accuracy. With foundation models, modern methods have moved toward mask-free approaches, leveraging priors such as Dino V2 for semantic appearance understanding and Depth Anything V2 for geometry awareness, enabling the model to infer shadow regions from geometric and semantic cues, reducing reliance on explicit shadow masks. However, we identify a critical problem. Even SOTA methods like OmniSR and DenseSR, which already integrate these priors, still fail to accurately localize shadows under complex lighting. As shown in the feature maps, their attention activations are diffuse and inconsistent. We believe the root cause is prior misalignment. Geometric and semantic features respond differently to illumination, and without proper alignment, neither prior is effectively utilized. This motivates us to better couple the model with these priors at multiple levels and generalize beyond single light to multi-source ambient lighting scenarios. We propose PhaSR, addressing the problem from two levels. At the input level, inspired by intrinsic decomposition and Redindex theory, which assumes an image can be decomposed into reflectance and illumination components. PAN separates illumination-related components from the input image, bringing shadow region pixels closer to well-lit regions. At the feature level, GSRA uses cross-modal differential attention to align geometric and semantic priors with the network's internal representations, enhancing object appearance understanding and geometry awareness for more precise shadow localization. Specifically, PAN achieves this through three sequential steps. First, gray world color normalization removes chromatic bias introduced by the illuminant by balancing each color channel to a neutral reference. Second, log domain Redindex decomposition separates the image into reflectance and illumination components, allowing us to estimate the global illumination and recover the pseudo-reflectance as the residual. Third, dynamic range recombination merges the separated components and rescales the result to a valid radiometric range, producing an illumination-consistent output image. The animation dynamically illustrates how PAN progressively corrects the input image through each of these three steps. As shown here, PAN improves the result at both levels. The corrected input already shows reduced residual error, and when passed through the network, the final reconstruction further benefits from this improved input distribution, confirming that PAN's correction has a positive cascading effect throughout the pipeline. GSRA takes geometric priors from Depth Anything V2 and semantic embeddings from Dino V2, injecting them into the network with learnable scaling factors. Two separate attention maps are computed, geometric and semantic, and aligned through differential rectification. This suppresses semantic over-smoothing at shadow boundaries while preserving geometric precision, producing a unified representation that enables accurate shadow localization. This slide presents the overall architecture of PhaSR. Experimentally, PhaSR achieves state-of-the-art performance on WSRD Plus and Ambient 6K, the most challenging benchmarks. On Ambient 6K, which features complex multi-source ambient lighting, PhaSR outperforms both dedicated ambient light normalization and shadow removal methods. Furthermore, PhaSR demonstrates the best cross-dataset generalization in both directions, confirming its robustness across diverse lighting conditions. Notably, all of this is achieved with the lowest flops among all compared methods, demonstrating that physically aligned design enhances both accuracy and efficiency. PhaSR effectively removes hard shadows while preserving fine-grained texture details and avoiding color distortion, demonstrating competitive performance against both mask-based and mask-free approaches on the ISTD Plus dataset. Moving on to the WSRD Plus dataset, our method effectively handles high-resolution indoor scenes with complex single-source lighting while maintaining photorealistic quality. On the INS dataset, PhaSR demonstrates robust generalization to synthesized indoor scenes with indirect illumination and soft shadows. Finally, on the most challenging ambient 6K dataset, PhaSR shows superior generalization to complex multi-source illumination and diffuse indirect lighting beyond conventional shadow removal, outperforming both ambient light normalization and shadow removal methods. To summarize, we present PhaSR, a mask-free shadow removal framework with PAN for global illumination correction and GSRA for geometric semantic prior alignment, achieving robust generalization from single light to multi-source ambient lighting with the lowest computational cost among all compared methods. Thank you for your attention, and this is our project page.